Hello everyone, welcome back to our channel. Today we are diving into another exciting topic, that is solving a system of ordinary differential equations using physics-informed neural networks with the DeepXDE library. This tutorial is a part of our tutorial series on physics-informed neural network. So this is our series. In this tutorial series, we explore solving different types of differential equations using physics-informed neural networks with DeepXDE library. In this particular session, we are focusing on a system of coupled first order ordinary differential equations. These equations describe how two variables x of t and y of t interact and change over time. So before jumping into the main topic, let me give you a detailed overview of what we will be learning today. First, we will understand how to encode this ODE system using residual equations. I'll show you how to use Jacobian functions to compute the derivatives involved in each equation. Next, we will understand how to define the initial condition for this sort of coupled system of equations. Next, we will configure the neural network parameters to approximate the solutions for the system. This is where the DeepXDE comes into play, helping us to minimize the residuals of the equations and find the solution. And after training the model, we will validate its accuracy. So here we are going to evaluate the L2 relative error on two different input data, and we will understand how changing the input data changes this relative error. And finally, we will visualize the results with simple and intuitive plots, so we can clearly see how well the physics informed neural network performed in solving this system of equations. As I said before, in each tutorial of this series, we are building the blocks together step by step to gain a complete understanding of how to use DeepXDE effectively. From solving simpler equations to tackling more complex systems, we are gradually expanding our knowledge to unlock the full potential of DeepXDE library for effectively formulating the physics informed neural networks. So I'm giving the tutorial series playlist link in the description. Please watch the previous tutorials to get the complete picture. So let's get started. Let's go into the main tutorial of this session. So these are the set of differential equations that we are going to solve today. So I have taken these examples from this particular website. So we can find these equations here. So this is where the equations are listed, and these are the analytical solution for x of t and y of t. So for these equations, we have an initial condition x of 0 is equals to 1 and y of 0 is equals to 0. And this domain is ranging between 0 and 5. Overall, this is a time domain problem. So x and t both are functions of t. That's it. So these are the analytical solution. Let's see how this analytical solution looks. Here I'm importing some libraries. So the DeepXDE, you know it, right? So this is the main physics informed neural network library, and a NumPy for performing some array and matrix operations, and matplotlib for plotting purposes. And here I'm doing some plot settings, and followed by here I'm plotting the analytical solution. These are the two analytical solutions. So if you plot them with respect to the time, so here I have just randomly taken some time between 0 and 5. So overall I have taken 500 values. So when I plot this x analytical and y analytical, so these are our solutions looks like. This is our x of t and this is our y of t. Our aim is to solve the set of differential equations using physics informed neural network and obtain a solution that closely matches with this analytical solution. As you have seen before, these are the two governing differential equations. Now we have to convert these equations into residual equations. And if you look at this equation, we have two derivatives, dx by dt and the other one dy by dt. So these are all first order derivatives, and we are going to evaluate them using this Jacobian. If you look at this Jacobian equation, here I is equals to 0 represents this x of t, and I is equals to 1 represents this y of t. So if you put I is equals to 0 here, the Jacobian outputs dx by dt. And if you put I is equals to 1, this Jacobian outputs dy by dt. After evaluating this derivatives, so here we are slicing the y for x of t and y of t. So this one represents x of t and this one represents y of t. Similarly, this one represents x of t and this one represents y of t. So this is that dx by dt plus 2x plus y. Similarly here dy by dt plus x plus 2y. So this is how we formulate the residual equations of equation 1 and equation 2. So when we are sending these two equations as a list of tensors. Here each element corresponds to the residual of one equations. Why we are sending this as a list? Because this structure allows DeepXDE to handle the residuals independently during the loss computation. After defining the residual equations, next here we are defining the initial condition function. So if you look at our original equation, so here we have two initial conditions, one for x of t and another for y of t. So at t is equals to 0, x equals to 1 and y is equals to 0. So these two conditions we are defining here actually. Both are initial conditions, meaning both checks for time at t is equals to 0. So here x is the input feature, and input feature here in this particular system of equations we have only one input feature, that is time, and at a time is equals to 0 or not we are checking this on initial. So this one is a boolean variable, true or false. So when this condition satisfies, then it returns a true, else in all other cases it returns a false. And after that here we are specifying the initial condition value. If this condition satisfies, for x we are applying 1 and for y we are applying 0, same as the conditions that was defined in the system of equations. After defining this initial conditions, so next here we are formulating the functions for analytical solutions. So here these first two functions, analytical x and analytical y, defines the analytical solutions for x of t and y of t. And if you look at here we are combining these two analytical solutions, analytical solution x and analytical solution y, into a unified function, that is analytical solution. Why we are doing like this is because to ensure the compatibility between model.predict. What happens is when we issue model.predict with a time, this returns a feature, output feature y, and this y contains two values, x of t and y of t. So here the first variable represents x of t and the second variable represents y of t. So in order to produce the analytical solution also in the same way, we are just combining these two things actually. We are just horizontally stacking the analytical solution x and analytical solution y. This analytical solution stacks this function x of t and this function y of t, so that both our analytical solution and this model.predict are analogous to each other. This is why we are stacking them here. This alignment simplifies direct element-wise comparisons for computing the metrics like L2 relative error. And also this stacking facilitates visualization as well. So in the end, when we are visualizing the results from PINN solution and analytical model, we no need to separately extract the variables actually, x of t and y of t. So we get both similar kind of solutions from both the analytical solution function and the model.predict. So they are easy to compare. That's why we are stacking them here. Apart from that, there's no special reason. And here we are defining the geometry domain. So here our domain is a time domain problem actually. In our earlier tutorials, we have tackled problems on pure spatial domain. In our recent tutorial, we have also tackled Burgers equation that is defined in a spatiotemporal domain. And in this tutorial, we are going to explicitly look at the time domain problem. So here, unlike in the previous tutorial, so here we are defining the time domain between 0 and 5. So here we are defining the initial conditions. So we are using this IC function, and this is the domain, and here we are giving the initial condition value for x of t, and here we are checking the is on initial condition. So it checks for whether the point is on the initial condition boundary or not. So if it satisfies, then it applies that value. Similarly, here it will check whether the point is on the initial condition boundary or not, then it will apply this y of t. Here, if you look at here I have specified this component is equals to 0 and component is equals to 1. In all our earlier tutorials, we have never used this component. If you look at our boundary condition and initial condition commands, so for example, this digit BC, we have a component. By default, it is 0, but we have a component. We have Neumann BC. Here also the component is 0. Robin BC, we have a component, and in the initial condition, we have a component. So in every boundary condition, we have a argument called component. What is that? If you look at our neural network, so this is our T input feature, and this is our output feature. One is x of t and the other one is y of t. Our component represents this thing actually. This is our first component and this is our second component. As in Python, indices starts from 0 and 1. So these two represents the two components that starts from 0 and 1. If you have more variables, maybe some n of t, we have a component up to n. So like that, you have to apply the initial or boundary conditions on a specific component, I mean the specific output feature. After defining the domain and initial conditions, so here we are defining our main data set, and for this data set we are using the PDA function in the data module, and here we are passing all the arguments here actually. So here we are sending the domain and the ODE system. This consists of two equations, equation 1 and equation 2. These two we are sending it via a function. That's it. And after that we are sending two initial conditions, ICX and ICY, and after that we are setting some parameters, num domain. So within the domain we are considering 400 points, and at the boundaries we are considering 2 points, and here we are sending this analytical solution. As you know, this analytical solution is used only for evaluating this L2 error. Apart from that, this analytical solution is nowhere used in our training purpose. And after that, for testing, we are using some 100 points. And here we are setting our neural network parameters. As you know, we have only one input feature, that is T, and we are using three hidden layers with 50 neurons each, and we have two output features. They are X of t and Y of t. And after that we are using this tanh activation function and glorot uniform initializer. And here, by combining this data set and a neural network into a model using this DeepXDE model class, so we are defining our model object, and here we are setting up the compile options actually. So the Adam optimizer and the learning rate is defined as 0.001, and the metric is the default metric L2 relative error we are taking here, and overall some 3000 iterations we are taking actually. So if we issue this model.train, training starts, and during the training it printed these kind of losses actually. So if you look at the original differential equation loss, initially it was some 4.14 e minus 1, and in the end it came up to 7.53 e minus 6. It reduced a lot. And if you look at our test metric, initially it was 1.72, and in the end, at the end of 3000 iterations, it is 1.37 e minus 3. So it was a decent value actually. And if you look at our overall results, so the train loss is 10 to the power of minus 5, test loss is of 10 to the power of minus 6, and test metric is of the order of 10 to the power of minus 3. So they are all decent values, and overall training took 14 seconds. And here, after we train our model, we have got our test matrix, right? So here, just to demonstrate how changing the test data, input data, changes this test metric actually. So here I'm taking this t test variable. So this is different from the testing data that was defined in this data set, and this data set I'm generating using this linspace function of this numpy. So here I'm generating 100 points, and these 100 points are different from the ones that was defined in this data set that was used in the training. So here, if I generate this analytical solution for this test values, and if I generate the PINN solution for the same test value, and if I evaluate the relative error using this L2 relative error, I have got some 1.46 e power minus 3. But if you look at here, the value is 1.37 e minus 3, and these values are different actually. And if instead of defining separate test data, if I use the test data that was used in the training and testing, simultaneous testing, so if I use that in evaluating this L2 relative error, so here you can extract the test data that was used in the training and testing here. So you can extract that using this data.testx. So this returns the input features that was used in the testing, real-time testing actually, that happens when you are training. So if you take that data and if you evaluate this y-test and y-pred, and if you evaluate this relative error, you will get this 1.37 e minus 3, and that is same as this one. This is one caveat actually. So next time when you are using external functions for evaluating this test metric, so if you get a slightly different error from the externally evaluated function and the test metric that was defined inside the compile options, so do not afraid. So first check your input test data. If they are same, then you should get the same value. If they are different, then you will see some differences in this L2 relative error as well. And next, after performing this cross checks, so here I am doing some result visualizations. So if you look at here, I'm generating some test values. So same set of values, but I'm generating twice for PINN evaluation and for exact solution evaluation. These are same values actually. And then here I'm evaluating this predictions, and here I'm evaluating the true solution from the analytical X and analytical Y functions. And here I am doing the plotting. So if you look at here, our analytical solution and PINN solution are exactly matching, and similarly in the y of t also our analytical solution and PINN solution are exactly matching. So overall we have got some good convergence, and our training is good. So that's all for this tutorial. If you have any questions or doubts, please feel free to ask them in the comment section below. I will try my best to help you out. If you found this video tutorial helpful, please hit the like button and consider subscribing to our channel. This will motivate us to produce more useful tutorials like this. Thank you for watching. See you in the next tutorial. Happy learning.